Okay, we're going to talk about simplifying radicals, specifically square roots. There are radicals other than square roots. This video just focuses on working with square roots. Okay, I'm going to show you two methods. The first method is sometimes called the 2-for-1 method. It's also sort of known as the factor trees method, because you'll make a factor tree. The 2-for-1 part I'll explain in just a second. You'll see where it comes in. Okay? And it's pretty much based off of this principle right here, is that the square root of a squared is equal to a. Okay, and it makes sense because squaring undoes square rooting. And if you notice, it's referred to as the 2-for-1 method because the exponent of 2 becomes an exponent of 1. So if you have two factors of a and you perform the square root, you wind up with one factor of a. Okay, so I'll show you this method first. If you get this method down as a theory pretty well, the second method is a bit shorter because you don't have to make the factor tree, and it can happen a lot quicker, but you have to have very good number sense and a good foundation in this theory first. So let's see what we've got here. I'm going to factor tree 24, and I'll turn it into 2 and 12, and then I'll turn that into 2 and 6. I'll turn that into 2 and 3. Okay? Then I'm going to use this 2-for-1 idea. If you notice here, I've got two factors of 2, and they shall become one factor of 2. If you notice, the two factors of 2 really is 2 times 2, which is 4, and the square root of that is going to be 2. Okay, now if you notice, I have these other factors here. I have one factor of 2 and one factor of 3. Well, there's no more 2-for-1 opportunities because I need to have two identical factors. So I guess I'll just put those back together and call 2 times 3 6. And that is inside the square root still because I was not able to square root either of those factors and simplify it. If we look at the calculator, we see that the square root of 24 gives us this decimal, and the square root, and let me bring that back. Then we have 2 times the square root of 6, which we don't need the time sign on the calculator, nor when we write it. If we see that they are both decimals, they are both 4.898, etc., etc. Okay? Now, interestingly enough, the decimal form is more useful at times, but it's not considered an exact value. The exact value here, when we simplify the square root of 24, is 2 root 6. Again, I made this factor tree, and anytime I had a pair of factors, I took 2 of them and made one factor on the outside of the root. The remaining factors that I could not pair up are multiplied back together and put inside the square root. Okay, so I'll do another example here for the square root of 98. And I know that that's even, so 2 goes into it in 49 times. 49 breaks into 7 and 7. So again, looking at the 2-for-1 method, I have 2 7s, which is 7 squared, that when I square root them, they shall become just 7 on the outside of the root. And then I have this spare 2, which I can't do anything with, so that will in fact stay inside the radical. Checking that on my calculator, I've got the second square root of 98 is almost 10, you see, because the square root of 98 is almost the square root of 100. So second square root of 2, okay, 7 times root 2, I see I get equivalent decimals here. So, more likely than not, this guy, 7 root 2, is equal to root 98. Okay, continuing on with these examples, I've got 125 is divisible by 5 and 25, and then the 25 breaks into 2 5s. And again, the 2 for 1 method says take the 2 5s, which is really 5 squared, and square root them, giving me just 5. And then we see that I have this remaining factor of 5 that's left on the inside. So square root of 125 simplifies to 5 root 5. You could verify that on your calculator. And for 48, we see in the next example here of 4, number 4, I can make a factor tree for 48, 2 and 24, 2 and 12, 3 and 4, and 2 and 2. Okay, now this one's a little different, but it's the same still. I'm still going to use this 2 for 1 idea, but you notice I have 2 pairs of 2's. So I've got this pair of 2, which becomes 1, 2. I've got this pair of 2's, which becomes another 2. Again, when I lassoed 2 of them, 2 factors, I take it outside the square root. If we notice, I had 1 factor left. It's the square root of 3. So I'll have to take a moment and simplify that, which gives me 4 root 3. And I could check that on my calculator and do second square root of 48. And 4 second square root of 3. And see that they're both almost 7. They're both 6.928, etc., etc. So, again, it's the 2 for 1 method. When you have 2 factors, you take 1 factor out, because the 2 factors, when you in fact square root, become 1 factor. Which should make sense that the square root of 3 squared is just 3, so we see how that tends to make sense. It takes a little practice, but once you get it, it's quite easy. I'm going to show you another method for doing these problems. It's actually a little faster. I used to teach this method first, but then kids were like, I don't really get it. I would teach the method I just showed you first, and then this method I'm about to show you second. People were like, oh, now I get it. So if you could come up to this method eventually, you're going to really be doing yourself a favor, because you'll be doing the problems much quicker. It's dependent on a couple of things. One is you have to know the perfect squares. You have to know them forward, 1, 4, 9, 16, 25, 36, etc. And you really need to know them backwards. Okay, 169 is 13 squared, 144, 121, 100, 81, 64, etc. backwards. You need to know them backwards because we're going to ask you an essential question here that you need to understand is, what is the biggest perfect square that goes into my given number that I'm taking the square root of? Again, what's the biggest perfect square that goes into that number? And if we want to say the biggest one, that's why we've got to think of them backwards, because the bigger ones are to the right. Now let's combine that with this idea. And it's, if you have the square root of a product, it's equal to the product of the individual square roots. And we've seen this, we can look at this as true, where you could say, okay, what's the square root of 4 times 9? Well, is that in fact equal to the square root of 4 times the square root of 9? And we'll see that this is the square root of 36, which is 6. And then this is equal to 2. The square root of 4 is equal to 2. The square root of 9 is equal to 3. And that's equal to 6. This would be true for any numbers that we apply this property to. So to state the property just again, it is in fact the square root of a product, the product being AB, is equal to the product of the square roots. So let's combine that with this question of what is the biggest perfect square that goes into 24? So if we work backwards from 24, well, here's 25, and then going backwards, 16 doesn't go into 24, 9 doesn't, but 4 does. I'm just going to really quickly split 24 into the square root of 4 times the square root of 6, which is equal to the square root of 4 times the square root of 6 by this property, which is just equal to 2 root 6. This part I put in the box. You could probably just skip that part and read it right out of this line. They are equivalent, so if we're trying to do this a bit of a shorter way, you don't totally even need to do that step. As long as you realize that you can, in fact, square root both of these numbers, well, that's why we picked a perfect square, so we can square root it and get the 2. So again, going on to the next one, which is the square root of 98, what's the biggest perfect square that goes into 98? Well, it's going to be smaller than 98. It's not 81, not 64, but it is 49. So I'm going to split 98 into 2 times 49. Probably even better to write the 49 first, because that's the number I'm interested in, but it's 49 times 2. Again, maintaining the square root symbol. And then what I like to do is say, well, the square root of 49 is 7, and I can't do the square root of 2, so I just write it. Okay, similarly on this next example, the square root of 125, which of these numbers going backwards goes into 125? Well, none of these do until I get down to 25, so I'll just split that into the square root of 25. If you're not sure what the other factor pair is, go on your calculator, but you should know that it's 5. And then I just say, well, the square root of 25 is 5. And the square root of 5 can't be simplified, so I just pull that down and leave it inside the square root symbol. So similarly, when I get the square root of 48, I start working backwards and realize, well, the number's got to be smaller than 48, so I'll start at 36. That doesn't go into 48, 25 doesn't, but 16 does. So I'll split that into the square root of 48 will be the square root of 16 times 3, which very quickly you'll see the square root of 16 is 4. The square root of 3 can't be simplified, so it remains in the square root symbol. And I'll have that. Okay? So let's take a look a second just to see these two ideas together at once, both these methods. I'll do one more problem. Okay, and to do that, I'll make sure I have this list here. Okay, and let me get a problem here. A good one is the square root of 72. Okay, and I'll do square root of 72 different ways. I'll do method 1, then method 2 over here. Method 1 said to look for the 2-for-1 idea with a factor tree. So I'll just make a factor tree and say it's 2 times 36. That's 2 times 18, which is 2 times 9, which is 3 times 3. If you're quick with a factor tree, this way's not too bad. Now I'm going to look for my 2-for-1s. I have 2 factors here of 2, which will become 1 factor of 2. I have 2 factors of 3, which will become 1 factor of 3. And again, when I lasso 2 of them, I pull it outside the square root. And then I also notice that inside the square root shall be this lone 2. So I'll leave that inside because it doesn't have a pair. And that brings me down to simplifying into 6 root 2. Okay, now, without the factor tree, just go grab this black cover up real quickly. Again, I will ask that critical question of what is the largest square root factor of 72, or what's the biggest square root that goes into 72? Well, it's got to be smaller than 72, right? So let's start at 64. Theoretically, I guess it's going to be smaller than half of 72 from a number theory standpoint. 49 doesn't, 64 didn't. 36 does. So real quickly, watch, when I split 72, the square root of 72 into the square root of 36 times 2, very quickly I'm just going to say the square root of 36 is 6 root 2. So when you compare these two methods, method 2 has a lot less writing, but it's also dependent on a good understanding of the number theory, of understanding that you can square root a square very quickly. So you also need to be able to recognize squares in terms of factors without making a factor tree if you're going to do method 2. So I hope that puts some clarity to how to work with square roots. You can always verify these on your calculator. Remember, the number you get on the calculator is not an exact value. These answers here that we got are exact values. Okay, it's a little bit of a confusing thing where you think, oh, I'll simplify it, I'll go to my calculator and get this decimal that makes more sense in terms of the number that I need to get, because you feel like 6 root 2 in this situation. You feel like, well, that doesn't seem simpler than the square root of 72, but it in fact is, by definition, of what we call simplifying radicals. So feel free to watch this again, feel free to practice, but also verify your answers on your calculator. That's a step in the right direction to help you master this skill. Okay? Enjoy.